Hello everyone, we'll start in 2 minutes.
Speaker sir, shall we start?
Yes, sir, we can start, sir. Pritham.
Yeah,
Yes, sir, sure.
we'll start then. Uh, Good evening everyone, I am Preetha Chaudhary and I'm delighted to welcome you all to the fifth day of the event, National Level Faculty Development Program on Advanced Statistical Techniques for Academic Excellence in Data Analytics, organized by the Department of Statistics and Data Science here at Christ University, Yashwanthpur campus. It is an honor to introduce our esteemed speaker for this session, Dr. Sumit Kumar, currently serving as an assistant professor in the Department of Statistics at the University of Delhi, India. With a distinguished academic and professional background, Dr. Kumar has contributed significantly to the field of statistics, particularly in areas such as statistical quality control, Bayesian inference, and data analysis. Dr. Kumar completed his doctorate in statistics from the Central University of Rajasthan, where his research focused on process capability studies, statistical inference, and applications that remain central to his scholarly interest. He has received several academic honors, including qualifying for the UGC National Eligibility Test, and holds a lifetime membership with the Indian Society of Probability and Statistics, underlining his commitment to advancing the statistical community. Dr. Kumar's teaching experience spans reputable institutions across India, including previous appointments at Chandigarh University and the Institute of Advanced Research. In addition to his academic contributions, Dr. shared his expertise as a guest lecturer, most notably delivering a 3-day lecture series on statistical methods for a Master of Design course at the National Institute of Design, Ahmedabad. His research is well published, with articles appearing in renowned journals indexed in Scopus and Web of Science, covering topics from generalized process capability indices to novel distribution models in reliability engineering. Dr. Kumar has also contributed to literature as an author with a notable book chapter on classification estimation methods and statistical quality control. He has presented his findings at both national and international conferences, showcasing his ability to bridge theoretical research with practical applications in industrial and statistical scenes. Today, Dr. Kumar will be leading a session on statistical quality control, a fundamental area in data analytics with wider applications in industry and research. We are privileged to have him here to share his expertise. Please join us in a warm welcome to Dr. Sumit Kumar. So, over to you.
Thank you, Professor. I'm audible to all.
Yes, sir, you are audible, sir. You are
Yeah.
audible.
Yes, sir,
Okay.
you're yes, sir, you're
Good evening to all of you. Thank you very much for the invitation to the organizing team, Dr. Sikar Tyagi and team, and
audible.
to
You're audible. You can carry on.
Gigi and the Christ Mystery as well. First of all, I will like to share my screen as my camera is not working there. If someone is know about the process, then let me know. Okay. Is my screen visible to all? Is my screen visible to all?
No, sir.
Let me share it again. Is it visible now?
Yes, sir, it is visible. You can start.
Okay.
Are you sharing the PPT or your screen, sir?
I'm just share the whole screen.
It's visible.
Okay,
Yes, sir,
it is
it's
visible
visible.
then.
Okay. Actually, this
It's
camera is
visible,
not
sir. You
working.
can start.
Is anyone known about the technique or how to we can on this camera? This
It's okay, sir. Without camera, you can continue.
okay. Basic topic today's we have statistical quality control. Throughout this FDP duration, we have already seen several topics like regression analysis, generalized linear model, time series analysis. Okay, and in that sequence, we have today the statistical quality control. Just we have I have just created the PPT including some photos or graphs, some related topics. Okay, so we will use some pen papers method also to make the classroom creative. Okay, and active. So first of all, we will as we know that we have to discuss about the quality control. So the first term we have the quality. So, whatever the things we are doing here or in the world or real life examples, we will, if we take from our personal life, so everything is based on the quality. So, what is the quality basically? Anybody? Like we are using the phone, mobile phones, okay, or we are using the laptop, we are sitting on a chair, we are using some chairs. So, what is the quality in these? We can say that means those terms, those products, or those services that is comfortable to us. They will be of good quality. Okay. So fitness for use is the basic definition that was given by the Zuran. So this
Sir, I
is
think your screen is not visible, sir.
okay. Let me my whole screen I have presented to you. Let me close all other windows. Are you able to see something on my screen? Okay, someone
Sir,
has tried.
just click on your PDF, sir. It is visible.
It's visible now?
Yeah, sir, it is visible.
Okay.
Just simply Control L, sir. Do then it will be in the presentation mode.
I have already done that. Control
Ah,
L.
that okay. Then fine, sir.
Okay, so we can say that quality means fitness for use. Okay, or we can say that whatever the product we are using, if this it if it confirms all the specification that was the required, that means it is in perfect standard of the quality. Okay, we are using the phone. The sound is not clear when you are using some music. Okay, so that is the sound quality is not good. Okay, so otherwise you can say that if you are using a pen, if it is not comfortable to write for the long term, okay, so it will not be the good quality. So whatever the things we are using in our daily lives, or any other product or any other services, whatever we are taking, okay, in daily uses, if they are not comfortable to us, they are not of good quality. So everything basically round about the quality. Okay, we are working, we are delivering a lecture. If we are not giving you the exact values or exact things that you are want, so it will not be of good quality. Okay, if you have taken admission and the teachers or the university are not supporting, and it is not up to that level that you have margin yourself, so if it will not be as well as the good quality. Okay, so quality you can define the basically that is fitness for your specification, whatever the specification you have defined for your product. If that is not up to that level, it will not be of good quality. Okay, so all the things we have around the quality. So to control the quality, we have to if this any product or services those having not of good quality, we have to control them. Okay, how you will control them? If we can say that if whatever the things you are creating there, or you are delivering a service, or suppose that a delivery partner of Amazon, Flipkart, or Zomato, if they will not deliver that product on time, it will affect the company service as well, and their review as well. Okay, so what you will do as a company owner, you have to take the action regarding what is the problems behind delivering the service. Okay, so you have to identify these problems to uh, so that you can uh, remove that basic problems in that specifications. So that quality basically you can control by using some you can say that tools and technique. Those tools and technique we can say like control chart, acceptance sampling plan, or whatever the tools you are using there, mean, median, mode, etc. They will be used to control the quality. So why we need the quality control? We can say that when you have to grab the market. Okay, so you have to deliver the perfect item or service. Okay, that's why we have to control the quality of any product or service. So if you are not reducing the means, if you are producing something like pen you are producing, or shoes you are producing, you are a cloth factory. Okay, so if some margins or errors are there, so you have to control them by using some method, that is statistical tools and technique you can say. So when you will reduce them, we can say the production cost will also be increase, production cost will be decreased, and the quality will be increased. Okay, and when you already know that your inspection cost, to reduce the inspection cost, you have to control your quality as well by using some tools and techniques. Okay, so statistical quality control basically you can say is a bunch, or just you can say that it is a method that collection that have some tools and technique to control the quality of the product. Okay, so we can say that if you are using a control chart to control the quality. So this is the technique you can say. If you are using the mean, median, mode, or something like a histogram you are preparing there, that will be the your tools to control the quality. Okay, and it may be defined by we can say that in two parts, like in process control and product control. We will come to there. Benefits of SQC, what you can say. If you have applied the SQC in some production, so what will be the benefit for the company? It will be maintained, improve the quality of the standards as that as the customer required. it will give you the correct product. Or you can say the frequent whatever the unwanted errors are there, you can remove them by using control chart or some other techniques. Or when the process is in control, so you can say the reduction of the wastage. Okay, it will be reduced, time will be reduced, and material will also be reduced. Okay, so this is the classification, you can say, of the SQC. We have to just focus how many bifurcation you can do with the SQC. First, you can say that means the process control and product control, two branches of SQC that mainly works. And in process control, we have process capability index or process capability analysis, control charts, and while in product control, we have to go for some sampling inspection plan. Just we have written here acceptance sampling plan. Just specifically we have written, I have written here, but it is basically the acceptance sampling plan. There are several sampling plans here, but we have just to focus on the single and double for this particular PPT. And control charts for variable and control chart for attributes we can study as well here. Basically, besides from these single and double acceptance sampling plan, we have multiple sampling plan, sequential sampling plan, okay, and some other sampling plans also in the literature, but we have to focus on these two. So why the if you have to control the quality, why the quality is so poor? What is the reason behind that? Anybody? Basically, we can say that you have heard about the errors, okay, or causes of variations like random causes, assignable causes, okay. So random causes, assignable causes, both are the part of this variation. Means why the quality of any product or service is varying. Okay, so there may be different scenarios or different background of their problems. Like in my one book, I have studied one example that was an introduction to the acceptance sampling plan by John Law. Okay, John Lotion, I think that was. Yesterday, one bookseller that gave to me, and I have seen that example there. What was the example? Example was that any person he have to drop his child to the bus stop, so the bus will come and pick up the child to take him school. Okay, so he have observed 30 days for the 30 days and observe the timing. Okay, and after that he just do some graphical methods to draw that how many time he have taken to pick up on an individual day. Okay, so he have just point out them like the days and the time durations. So he have observed that, so for particular 2 or 3 days, he was too much late. And when he asked about the reason, so there was some specific reasons were there. Like for one day, there some cracks or so you can say some accidents was happened with that bus. So for another 2 days, the shift of the driver was changed. Okay, so we can say that besides these 2 or 3 days, all the other things were the same. Okay, means slight difference were there. Like if he has to pick the child 8:15, so it will be 8:20 or 8:25 up to 8:10. Okay, like that. So we can say that some specific variations are coming due to some specific causes. Okay, like 2 or 3 days, as I have mentioned here. So we can say that there were some special causes. Okay, or some we can say the assignable causes that happens in the process sometimes, that that basically you can say reduce the quality of the product, or your product will be out of control when you will draw the control chart. Okay, and there are some common causes. Common causes like you can say the common causes means random causes. That may be the inaccuracy in the data. Okay, or when we have collected the data, some inaccurate value that we have mentioned, measurement tools. Okay, that he has introduced natural fluctuations. Okay, some environmental like rainy days, it is so that will be late. Okay, or some assignable causes that will be the machine failure, human error, materials variability, environmental factors. Like if you will talk about the medical sectors, so there were some specific if some uh, descriptions was given by some doctor, and you will go to the store, medical store, and you will buy the medicine, particular medicine that he has mentioned. So sometimes you have seen that the store persons have told you that this specific medicine is not there, but we have some other medicines from other companies for the salt or same. Okay, that medicine will also work the same method. Okay, but company is different. So these make we can say that this will be random causes. Some slight variation will be there. Okay, but that will work as he has mentioned the some other medicines. Okay, so we can say that the causes of variation are the main part of SQC or statistical quality control that we have to maintain. Either you will talk about the statistical process control, either you will talk about the product control. In both the cases, you have to basically control the quality of the product. Okay, so we have two branches like statistical process control and product control. So statistical process control, what basically we do, these two branches work parallelly. Means first the product will be ready. Okay, after the product has been prepared, it will be ready for the departure to the customer. Okay, like you have ordered some pizza or some burger from the Domino's or Pizza Hut. Okay, so it is, you can say that when the process is going on, when they are preparing their product, okay, some error can be happen, like they have mix up more salt as usual, they are using, they have mix up more salt, more some other things. Okay, or some other casualty will happen with them. That is the error happen during the process when it is going on. Okay, so it will come under the statistical process control when your product is ready. Okay, so they will call to the delivery partner, and delivery partner pick up your order and deliver to you. That is the product control. So they will before delivering the your product, they will also check that whatever the specifications or whatever the items menu you have decided there, all the things are inside the packet or not. Okay, so that parts come under the statistical product control. So we have to control both parts, statistical process control and product control. Statistical process control basically important to us, like that if you are producing some products, and when this process is going on, if you are not able to control that process, so your wastage will be high. Okay, otherwise you means you can say that whatever the material you are using, that will be waste, your time, your labor, your money. Okay, everything will be waste. So when the product is under control, means when the product is under process, when it is making company is making something, so you have to control there. So your you can say the you can efficient your work. Okay, you can gain more profit, like that. So statistical process control, we can say it can be achieved, or it can be achieved through the some other methods, like by using the control chart and process stability index. They are the main part of this statistical process control. And we can say that statistical process control is a process when we have to control the quality of any product when the process is on. Okay, or it's going on, like that. So basically, control chart and process stability index, we have two different things, but their main work is to control the uh, quality of the product. Or you can say that they have to remove the assignable causes, because random causes, some whatever the random causes are there, they will be inherent. You can't remove that at much level. Either you have to come change the product, okay, or you have to change the machine if that produce something. Like if there are two different pupils, and they have different ability to work, like that. So they have different ability, they have different work culture. Okay, either you have to remove them, either one person will work there, so that you can remove the random causes. Otherwise, no. So assignable causes you have to remove when the process is going on. So control chart, what basically control chart do? When you have process is going on and you have to collect some random data. Okay, like by using some interval of time. Okay, then you have to draw that data on the graph by using the control chart techniques. There are some, we can say the limits are there, control limits, three sigma limit, specification limit, tolerance limit. We have to take all the things together. So after controlling that, after drawing that, you will just elaborate that what is your process. It is in control by seeing that, by seeing the graph. Okay. And the other thing that we have seen, that is the process capability index. That is the particular measure that identifies how much the process is incapable. Means it is capable or not capable. And how much it is capable, how much it is incapable. Just exact value it will provide you. Okay, so these are the two different things. So we have specification limits are there, tolerance limits are there. What are these? Let's see one example here of the graphical method we have just shown here. You will see some random graphs here. I have just taken whatever the pictures or examples I have taken. I have taken that from Montgomery book. Okay, Introduction to the Statistical Quality Control by Douglas C. Montgomery. Okay, so you can use that book also. And whatever the R code I have used, that will be for the same problem. That mostly same problem. Otherwise, we have taken from the online so that it will not be difficult for you to find the problems. Okay. So you will see here there are some specification limits. You have the lower specification limit and the upper specification limits. Specification limits, you basically can say that it will be the part of the specification that are desired or required by the customer. Okay, that is already defined by the customer. Means if you are you can say that if you are producing if you are producing something or you are buying something, like you are taking the laptop, okay, or just for uh, daily work example, if you will take, you have to take the you have to purchase the sofa or bed for your particular use. Okay, so you have particular house or the room for particular dimensions. So you have to tell to the carpenter that for this specification or for this dimension I need the this particular sofa or this particular bed. Okay, like 2 feet 6 feet long and 3 feet width of bed is should be there. Okay, like or the sofa, whatever the dimension as per your room you have at your home. Okay, so you have given some specifications like that. So those specifications you have given, those are the lower and upper specifications. Means the length should be like 5 meter or 10 meter or 6 meter, like that. Beyond that I will not accept. And if this is a slightly bit for the inside the capability, inside these limits, that can be manageable, but outside of this it will not be manageable. So basically specification limits, you can say, can be defined by the customer. While you will see here in these three different graphs, this is the natural tolerance limit. L and TL means lower natural tolerance limit and upper natural tolerance limit. Means whatever the data you have collected from the process, when you have taken to the graph, you have created the graph for that, like control chart. So control chart, and you have just find, you have taken some limits are there. Okay, either you can take this is the basic method of controlling. You are taking the limits mu plus minus 3 sigma. Okay, so you have taken just specific limits mu plus minus 3 sigma. If those specification, whatever the samples you have collected, all the values are whatever the process you have taken are inside these limits. Means this is the process you have taken here, and this is inside the 3 sigma limit. So these will be the, you can say, the lower and upper natural tolerance. Okay, have you got this? The basic difference between these. Any question up to here?
Sir, I have one question.
Yeah.
when we have that one upper tolerance limit or lower tolerance limit, then why we need this natural limits? Is it some that
We these the things we are not required, but these are the limits that are that we have from the process. Means whatever the things you are taken there, mu plus minus 3 sigma, you have done something, some calculations are there. So whatever the limits they have created by this interval, like mu plus 3 sigma, mu plus sigma, and mu minus 3 sigma. So whatever the lengths you have taken 6 sigma here, the total length will be the 6 sigma. So this is the basically the process, okay, based on the data. Okay, based on the data, whatever the things you have taken here, that is the Six Sigma. Means you have to compare them with the upper specification limit and the lower specification. If these limits, you can say that this one, and this one here, all things, all the three graphs you will see here, 1, 2, 3. Okay, in these all the natural limits are inside the upper and lower specification limits. Sometimes what happens, if you have like this graph you will see here, this is your lower specification limit and this is the upper specification limit. But here what happens, here the process mean mu, okay, and here the process mean is mu1. It means your process has been shifted to the left side. Okay, or you can say that your process has been shifted to the left side, means the lower natural tolerance limit has gone to the lower specification limits. Okay, if we can say that if you have to draw the control chart like this, CL, LSL, this is the LSL, this will be USL, and this is CL, control limit, lower LCL, UCL. So this is the control limit, lower control limit, and upper control limit, or you can say the natural tolerance limit. Okay. So when you have to draw the graph here, in this case, what happened? This limit has gone outside this. Okay, means up to here. If this is inside up to here, it is fine. But whenever these limits are gone outside, you can say that your process will be the out of control. This is the indication that the control charts give you. Okay. So basically you have to compare your natural tolerance limit with your specification limits. Are they inside or are they outside? If they are inside, both sides, so it will be fine. Otherwise, you can say that will be not acceptable and you will not take the product or you will not buy the service, okay, for the vendor. So you can say that one thing I will mention here, that if they are the USL and the LSL, lower and upper, sorry, this is the LSL and this is USL. If your process something like that, basically, okay, and somewhere at this point, your natural tolerance limit lies. Limit, and this is the lower natural tolerance limit. So you can say that your process on both sides, on lower side and upper side, means you have the out of control point from the control limit, upper control limit, and the lower control limit. So this product will not be accepted. This is something you can understand, like that you are making some food and you have taken too much salt in some particular vegetable or whatever the things you are creating there, you are making there. Okay, if you have mix up the more salt, it will be useless for you. If there are less salt, you can mix up that. This is something like that. So all these three graphs, you can say they are under control. Okay, if what happens here, the process means it means whatever the specifications you have given, all the things are under that specification, not beyond that. So that's why we can say that the specification limits and tolerance limit, we have some relation between them. Like if we will talk about the process capability analysis indices, that is CP, CPK, or some other indices are there, like CP we have in this slide as well. Let me take to there. Just on this. So basically, a process capability, what we will do, as we have discussed, there are some limits are there. We have to control that by using by controlling the variability. That is the same thing we have written here, nothing else. So that's the thing I just want to explain the process capability index in that point. That is basically we can take here. Suppose that is CP. In the next slide we have that USL minus LSL divided by 6 sigma. So this is nothing. PCI process capability index is nothing but you can say the ratio of the specification limit and the design. Okay, or you can say the specification to the tolerance. 6 sigma is what? 6 sigma you have taken from the control chart. Whatever the limits you have taken, mu plus 3 sigma and mu minus 3 sigma. When you have taken the length of this interval, this will be 6 sigma, and this is the tolerance limit. Okay, this is the ratio of that. There are several available indices, possibility indexes in the literature. They have some slight modifications there to define and to control the process. If we have different kind of problems in the process to tackle that. Okay, so we can say that process capability index is nothing but the indices that control or that elaborate the method that tells you that how much process is capable and how much not. If we will talk about this one, sorry, this one process CP1. The first measure we have the this one, the first measure Zuran given by the Zuran. And just we have taken here U and L that are basically the lower and upper specification limit, and by the natural tolerance. If this value is 1, you can say that this process is exact equal. Means upper specification limit and lower specification limit both are equal. So the process will be good. Okay, there is no need to do anything with this. If you can say that if this is basically you can define it as just this is greater than 1. Okay, so when it will be greater than 1, tell me, anybody? And the lower part or denominator part will be less, so the upper part will be high. Okay, it means that whatever the process you have created there, if these are the USL and LSL, and then you can say that your process will be inside that. That's why you can say that this will be greater than 1. Means whatever the value you have taken, this is inside that. It is good for you. Okay. If we get for the third example, if you will write here, this is less than 1. What is the condition for that? You can say that when the natural tolerance limit are outside the, you can say the USL and LSL. This is the case actually. Okay, so in the literature there are some other process capability index also there. That is K9086 introduced second generation capability index. That is CPK. What is the difference between them? As you will see here, there is no process mean. Means if you have defined two process here, this one and uh, this one like that. Okay, so you will see here somewhere somehow this process mean that is mu. You can take it is mu. Okay, and this is you can define mu1 and this is you can define mu2. If your process has been shipped, so you can't identify by this measure. Okay, so it means your process has been shipped from the center value that you have defined. So to overcome this difficulty, CPK come there to identify the problem, and he has included the process mean and the process mean with the upper and lower specification that bifurcate both the limits, that is 3 sigma and 3 sigma. Okay, and whatever the minimum value over these two separate values, okay, first one and second one, you have to take that to find the values. And if you will compare with the CP and CPK, obviously if the your node process is normal, in that case they will behave somehow similar behavior it will be there. And if your process is not normal, then you have to go for the you can say that this will be the reliable in that case. Next, we have some other measures. That is CPM and CPMK. These are the CPMK is the generalized measure, and means whatever the things you have taken last time, that is the process mean is not there, but some target value is also there. Whatever the process mean, that is the different thing, the different thing. But some target value means whatever the specification you have defined, that is the target value. Okay. If the process is shifted from the target value, that will be the out of control as well in this condition. So CPM comes to overcome this drawback by using the target value that tells you the how much process have been shifted from the target. And the CPMK just you can say the higher part of the CPK that gives you the minimum value of the upper and lower specification limits. Again, what is the requirement to we can say directly the to reduce the cost, reduce the to for the loss of the materials, okay, to reduce the manpower. We can say that's why we use the process capability index. Okay. Next we have control charts. So whatever the things we just going through the control chart, just basic definitions we have just included here. We have already discussed. This is the basically upper specification limits and center line and lower specification limits of the control chart. On the upper side, you on the y-axis you can write basically uh, uh, the sample numbers. Okay, sample numbers on the x-axis or groups. How many sample number or sample groups are you have, and their particular either you have to point the values if you have taken the sample, and if you have taken the sample subgroups, you have to mention here the mean of their subgroups, particular subgroups. This is basically just how to make the limits we have defined here. In this, you will see we have central limit here, UAL lower limit and upper control limit. This is nothing but the, you can say if you have collected the data, you have to estimate the values. In that case, that will be the X double bar. If you have taken the sample subgroups, okay. And this will be X double bar plus K stands for here some constant value there, okay. That is basically you can define how much process, how much deviation you are taking from the central value. That may be the 2 sigma or 3 sigma limits. Okay, like that. Minus 3 sigma. If you are using the X bar chart, that will be the standard error. So it will be undo 10. Okay, so we can define it as this is the process plus some deviation, constant are there with some standard deviation or standard error in case of samples you have taken. Okay. Are you getting all of you? This is one example just for your to show you. We have just taken one photograph for the control chart. We have some sample values and average thickness of that example. In this average values means, and we have just pasted these average value in the control chart by using the USL, LSL, and CL. Okay. Next. Yes. Hypothesis testing part will also be included in this portion, as when you have to take decisions, you have to make some errors also. Okay, so it also happens in this case. So when you have taken some samples, you have draw the control chart, and okay, and either it will be in control, or either it will be out of control. Sometimes it happens that whatever the points you have elaborated there, you have shown there, fixed there. So these showing you the in control, but actually it is out of control. Okay, so these type of errors happens, and we call them the type first error. So type first error means alpha, probability of type first error alpha, you can say defined by alpha. It will be, you can define it as risk of the point falling beyond the control limits, indicating that indicates that your some assignable codes are present there. Okay, means it indicates that is in control. Okay, beyond the control, but it is actually in control. Second, conversely, we can say that the type second error, what it will be happen? What will happen to that risk of point falling between the control limit when they are actually out of control? Okay, so these type of errors happens in the when you are drawing the control chart or taking decisions in quality control. This is the full example I have shown you here by using the photo from the Montgomery book. Okay, you can see that in this as well, you have seen when you have taken the normal process in this case, just here, when you have taken the normal process, okay, two-sided case you have taken. So this portion goes outside from this point and this point. Okay, if you have taken 10,000 points and you have taken the 3 sigma limits are there, so you can say that how much confident you are. If you have to do the confidence interval 99%, how much area it will cover? Tell me. 99.74%. Okay, so actually we can say that out of this 26 product will be the defective. Okay, two-sided case you have taken, so the half error you have shown on the that side and this side. It means when you are taking the limits, you have to define, means if you are increasing the side, means you are taking the 4 sigma, 5 sigma, or 6 sigma. 6 sigma you have heard about that, means when you have to like some companies, airplane companies, those work to produce the parts, okay, their risk is high, so they use the 6 sigma, okay, to reduce the error. Otherwise, we have to just focus on the 3 sigma limits where we have to define 99.73%, 74% will be inside the control limits, and with that much means 99% we are confident with that. Some probability statements are there. So these type of errors also happen in this case. To solve this problem, just elaborate here that the type of error will also be happen in the quality control. The same example is continued here. Now the rational subgroups. What is the rational subgroups are there? Why we have to use rational subgroups? Like you can draw the control chart by using the sample numbers. Means single samples you have taken and you can draw that. Some points you will be there, but sometimes it happens some individual errors are there. Okay, that is you can define like a one person working more than 8 hours from their shift. Okay, that will be tired, and when you have taken the sample, he has done some mistake. Okay, so when you have taken single samples, these kind of errors will be come there. To remove these, we have to focus on the rational subgroups. Rational means we have to, if you are some company producing some parts or some product, something on different shifts on different machines, so you have to take samples from different shifts, from different machine as well, from different time period. Okay, so whatever the time period you have defined there, that is basically depends how much process you have that is in control and out control. If it is not much out of control, then you can you can say that you can take the more time to take the sample or inspection. Otherwise, you have to shorten the time. Okay, so frequently you will take your samples. Okay, so that you can margin you can see the product. Sorry. Okay, so rational subgroup, I think you have understand. Now the pattern of the control chart. Sometimes, as I said, you sometimes a control chart shows you that it is in control, but actually this is out of control. Or this shows you the out of control, or otherwise it will be in control. So analysis of the pattern of control chart will also be useful for you. Some kind of patterns are there. All 6 or 7 points are around the center line, or some cyclic trend is there, or upper trend or lower trend are there. So these kind of patterns should be there. You have to identify to find the control chart that is giving you the exact value or depicts the exact in control process. So if you have to check the efficiency of the control chart, you have to use either OC curve, OC function, operating characteristic function we can say, and the average run length. What are these? These basically we can define somehow this is related to the alpha and beta. If your process is in control, so you can say that average run length will be that will be 1 by alpha, average run length, ARL. If your process will be out of control, then it will be 1 minus beta. So you have to calculate your alpha and beta. That is the, you can also define, if we will talk about the product control, if there it will be the producer or consumer list, both we have to discuss there. And here it is probability of acceptance, AQL, in terms of product control, we can define this. So this will OC curve and ARL you can use in both sides, process control and product control. Their meaning will be different, but things are same. Like a person can be parent, okay, can be father, can be child, can be husband, like that. Alpha and beta role are different, but things are same. Here you will see the OC curve. Let me explain here. This is the 1 minus alpha, or you can say that this is the producer risk and this is the consumer risk. Means if you have to see the perfect example of the OC curve, so it will be something up to here. This is the average outgoing quality. Okay. Whatever the quality you are taking, just this will be the acceptable by the consumer. Up to here, that will be acceptable. After that, after this point, beyond this point, you can say beyond this point, this will be rejectable, and this will be the decision criteria. Means either it will be accepted or rejected based on the consumer perspective, you can say. And this is the producer risk, means some good quality product is there, okay, and that will be rejected. So that will you can show that here by using the OC curve. That is the producer risk, and this is the consumer risk. Means bad load had been accepted by here. This is the average run length basically. Means how much samples you have or you require to get the how much inspection or how much samples are required to get the decision. Now we have to basically focus on the control charts. Two types of control charts we have. Just basic examples I will take here. Variable control chart and attribute control charts. Variables means those are measurables. Okay, and you can say then length of the pipe. Okay, weight of some particular persons. Or continuous values are there. If they are continuous, so in that case we can define some basically control chart for mean and variance, or mean for mean and range. Both will be discussed together. Okay. Control chart for attributes, we can define them separately. Okay. Attributes means some quality are there. How in the last 5 years, how was your preference? That was good or bad? Okay. These kind of things will be discussed in the control chart for attributes. But when we are talking about the mean chart, range chart, standard deviation chart, they are basically different but used in a same fashion or same manner. If your sample size is, you can say, large, so you can go for the standard deviation, because the range will be include only two values. It will not explain you the much information about the data. Okay, and if the sample values are less, so either you can use the range or deviation with the mean chart. So just we have taken basically some standards we have given here, but there are some specific we can say procedure to draw the control charts. What is that? What is that basically? Means you have collected the samples, as you have either you have taken individual value, either you have taken some sample groups. So from that, if you have taken the sample groups like 1, 2, 3, 4, 5, and so on, and in one sample you have 5 observation or 4 observation like that, like A, B, C, D, like that. So you have to take first the average of the each individual. So you can define x1 mean, x2 mean, and so on. And after that, you can find the combined mean for all these, for all the sample groups. Okay, this is the procedure, and the same thing you have to do for the range and standard deviation. You will get the range for the different samples, then you will find the mean of the range, and then you will find the mean of the standard deviation as well if you are taking the sample. Otherwise, you just define mu plus minus 3 sigma. These are the control limits. You can work directly with them. Okay. Some constant values will also be there by different books having different notations. If you have some like mu plus 3 minus sigma plus minus sigma, they have modified, some changes are there. Like if you will say x bar chart, so it will be sigma by root. So we have taken mu plus minus a. Suppose a we have taken here, that is sigma. So a we have taken the this constant value. Okay. So these are the constant value. They are already given in the R packages and as well as in the books as well. Means that depends on the sample groups and their size. How much size you have, that you define your values basically. Okay. So just basic things we have discussed here for the X bar chart. If you will take, so we can define this will be mu plus sigma, mu plus minus. If you have taken basically sample values, so what you will do here, that is the mu plus minus 3 sigma by root n. That is the standards when the standards are given. Otherwise, what you will do, x double bar plus minus 3, whatever the deviation you want to take, either it will be 1 sigma or 2 sigma, and this will be whatever the standard deviation s you have taken by root n. Okay. Similarly, you will do for the R chart, S chart. Okay. And when the standards are given, we both are the same. I think we have placed the same photos. Okay. These are the different photos over there, but I think I just in copying. These are the same. So these are the when the standards are given and when standards are not. Okay. Now we have control chart for attributes. So basically control chart for variables are simple, and you can define just one process is there. You have to put the values or you have to put some constant values. You will get the values. You will get your answer. Okay. But in control chart, you have some specific values. Okay. Control chart for attribute, you have to discuss about some, you can say some defective items. Okay. Some conformities or non-conformities or defective, non-defective. Okay, or some quality or some attributes. So first chart that we have, control chart for fraction defect. Fraction defective means you have some product, okay, and in that product some defects are there, and that defects includes in one product combinedly. You can say that this whole product will be the defective product. Okay, where D we have taken the proportion P equals to D by N. That is nothing but the ratio of the number of defective to the sample size. Means the proportion you have just kept. Okay, when the standards will be given directly, the standard values you will here. Like there are 5 defective items out of 100 samples. Okay, so just you have to put the values 5 by 10. You will get the proportion P, and you have to use the value. You will get the answer. When the standards same we have mentioned here. Okay, when standards are not given, just take it as not given. So in that case, what you will do, you have some samples. In that case, you will calculate the mean of that proportion. P bar, it will be there like that. Okay, just formula you have to put the values. This is the control chart. Next, we have control chart for the defects. Means in a product there may be more than one defects. Okay, so whole product will be defective and there will be defects. So if you want to study the if you want to study the same product, that will be fine. If you want to study some specific characteristic, that will be used under the number of defects, means NP chart. The formula will be same here, just that we have taken there this value. So D will be here NP. Okay. So in case of that, you have to use here standards when given. So NP directly we use NP plus minus 3, NP 1 minus P. And what is that P? Basically, you can say number of when you have to talk about the number of defectives that use the basically binomial distribution. Okay, so whatever the things you are there, that they are come from the, that is the mean of the binomial, that is NP, and variance is NPQ. The same thing we have mentioned in both the charts, in the defective and defects. Okay, that will be used under the binomial distribution. Next, we have chart for defects. It will not be per unit. Control chart number of defects. Just 20 seconds. Some errors are there. Per unit chart is I think that is for U chart. Some misprint are there. Maybe. Anybody can tell me what is the error here? Is it fine or some error is there? Basically, per unit, when we have to discuss the per unit, this is misprint actually. That is the U chart. Okay. Sometimes we can say that the variables number of sample size, whatever the samples you are taking, that is also a variable. In that case, you have to discuss that per unit how many defects are there, number of defects per unit. Okay, but it will be the number of defects only here, so it will not be there. So that is basically use the Poisson distribution. Okay, because there are several defects in one product. You can say that the probability of you can say the occurrence of defect is here is very rare event. Okay, so that it will follow the Poisson distribution, and you can define these three sigma limits by as you have c hat will be lambda. So we have to use here the lambda because mean and variance both are lambda. So in place of these, you can just directly use the standard values. If you have to calculate them, then you can use the C bar. Okay, this is the C chart, and the same thing you can do. Same limits you can define with the U chart. What is that? You have to just whatever the C bar you have taken by number of values Ni is there. Okay, so variable sample is also sample size is also a variable. In that case, when you will draw the control chart for that one, so that will be means actually these comes LSL, so LCL, CL, and UCL. Straight line for other graphs. When the size of the sample is variable, so when you will draw the limits or draw the data, that these graphs will also be variate like that. Okay, for some sample size it will be here, for some sample size it will be here. So the limits will also be varied in this case. Now we have a statistical product control. Okay, what is the statistical product control basically? As we have discussed, there are two parts: process control and product control. When the product is already ready and it is ready for you can say for the delivery, so that will be you can say product has been ready by using the some tools there are technique, that is the sampling inspection plan under the product control. Okay, so we have to basically discuss in this section the inspection plans. That may be 100% inspection, or either you can say it will be used for the sampling inspection plan. So this will be work as same you have used the word population and sample. If you have to study the whole population, what are the consequences are there already knows. Okay, everyone knows about this. So when we have to go for 100% inspection, we can say that we have some problems. Sometimes it is not means a study variable. We have to want quick results. Then we have to go for samples. Okay, 100% inspection only be you can say crucial when you have to check like aeroplane parts, when there is no error should be there. In that case, you have to go for 100% inspection. Otherwise, sampling inspection is there. Okay, like if you have to check the quality of the crackers or bulbs. Okay, so if you will test the crackers by using all of them, so what you will sell, what the producer will sell to the customer. Okay, so sometimes 100% inspection is not required. We have to focus on the sampling inspections. Sampling inspection as well are different type: sampling, single sampling plan, double sampling plan, sequential sampling plan, multiple sampling plan as well also there. Okay, inside them, rectification sampling plan. When we have either accept or either reject the data or reject the load. Okay, so if it is accepted, so whatever the you can say the default or faulty products are there, you will replace them or you will remove them. And when you have to reject, means some defects are there and you have specified some quality standard, and beyond that you will reject the load. In that case, that will go for the inspection plan. That may be the 100% or either sampling plan. Okay. By before going inside this inspection plan, there are some we can say tools, okay, or terminologies are there, okay, that we have to use. That may be the first is load quality. What is the load? You can say that load size or load quality. Load size is different. First, we can take here the load size means 100% values or the whole product, capital, and you can define it as. And load quality, sample size also there, that is smaller, that is there is no need to define that. Load quality means you have some products, okay, you have taken the sample. When you have to talk about the some sampling inspection plan, some N is there, you have taken the sample. In this sample there are some defective items, okay, you have identified them. If customer's parts comes here, if the if you have defined some C is there, let's say this is acceptable quality of the defective product. Okay, if you are purchasing some 100 product of something, and in that 5 are defective, okay, and 95 are correct. So you have just defined here alpha equals to 5% like that. Okay, and if it is less than this, D is less than this, C, so you can say that this will be accepted. If D is greater than this, D greater than equals to this, you will say that this will be rejected, the load. This is basically the single sampling plan. Okay, so basically what you can say, load quality will be the P, that is the number of defective units in the load. Units in the load divided by the load size, capital L. So P you have to calculate in when you will use the R program. I have not much explained there. Means by written that what is the P, what is the PA. Just that's why I am just explaining this. Okay, so P, this is the load. You can say the load quality we can define there. Acceptance number we can say that sometimes. Okay, acceptance number will be the maximum number of allowable defective units in the samples. Means customer can define C, P, P is there, some specification, some proportion defined by the customer. That is your acceptance number or acceptable number. Then we have probability of acceptance, LO. Probability of acceptance means what are the samples you have taken that will follow some particular distribution. Okay, means you have to define some defective are there and you have to take decision by using condition C. Okay, and that particular data following some distribution that you have defined here, probability of A by using particular proportion of the quality. Okay, or you can say that this is the probability of getting some particular value or extended derivation you can see. For a particular case, as these are the quality, these follows the first hypergeometric distribution. Second, it will follow binomial. Third, it will follow Poisson. Why these three? Hypergeometric means some defective loads are there and some non-defectives. Okay, that will follow the hypergeometric distribution. But some cases, what happens, the load size is too high. Okay, and if load size is too high, and this is multiply of 10n, whatever the sample size you are taking, it is greater than this number, then you can go for the binomial distribution direct. Okay, and as you know, binomial distribution also proxies to the process distribution as NP is finite, that is lambda. Okay, and the probability of some rare event you can say. So in that case, this will follow the Poisson distribution. So whatever the things you have defined here, this is the probability of D less than equals to C. You have to find this value by using these specific distributions. Are you getting? So basically, we can define this probability something like X less than equals to C, that will follow the distribution of hypergeometric distribution or binomial distribution. Okay, something like that. Next, we have acceptable quality level. What is that acceptable quality level? This is basically, you can say, the proportion of defective units. The proportion of defective units whatever the loads you have taken in that, and it will be less or equals to the AQL. AQL, what is the proportion defined by the customers? Okay, or you can say AQL will be the quality level of the good loads. Okay, so this is something you can remember that for good loads. When you have seen the OC curve there, so this was the graph, and somewhere at this point, this was the AQL. So good load will be accepted if it is up to this portion of defective items. Okay. Next, we have load quality or rejectable quality, or sometimes it is also called as load tolerance percentage defective. Okay, that is LTPD. So when you have to define the OC curve, this will be here RQL, rejectable quality load. Means if you have defined that out of 100, 7 product, if there are defective, I will not take that product. So it will be your basically IQL, or just you can define this is P2 something somewhere. Okay. Next, we have producer risk. What is that producer risk? Basically, this will be alpha, that is nothing but the probability of rejecting a load of quality AQL. Okay, whatever the quality AQL, or just if you will define the proportion of defective in that particular term, that is suppose that is P1. Okay, so you this AQL will be the P1. Okay, so either you can define it as it will be 1 minus probability of acceptance a load, accepting a load of AQL quality or P1. Okay, so you can basically probability of acceptance you are defining. As you are defining, this was the probability of acceptance, that is PA at the P1 level. Okay, if you have to find the beta consumer risk, that is beta basically. In that case, that will be the probability of rejecting. So this will basically probability of acceptance at the level P2 that we have taken here. So P1 and P2 we have defined, that is AQL means that is acceptable, and LTPD or LQL or RQL will be the P2 portion of defective items that you can define here. So this will be basically alpha, and this is basically beta, or producer risk or consumer risk you can say. And these will be basically calculated by using the same distribution as we have discussed, hypergeometric, binomial, or Poisson. So somewhere you have seen someone use our hypergeometric distribution, either someone is using binomial or someone Poisson. So this is the reason behind it. Okay. Next, we have operating characteristic curve. We have discussed this, that average total inspection means to get the decision or to reach the decision. How much sampling inspection, how much samples we have to inspect before reaching to the decision. This is the average total inspections. Average sample numbers mean how much sample numbers are required to get the decision of acceptance or rejections. Okay. And beside this, these were the basic terminologies that will be used in acceptance sampling plan. I think all of you have got this. Any doubt up to here?
Sir,
Yes.
Dr. Sumit sir.
Yes, sir. Boliye.
Sir, I have a query that you just told regarding when we use hypergeometry. Can you please repeat that? When we use hypergeometry distribution?
Actually, when the load size is too high, multiply as we have given the specific value, that is multiply of 10n.
Okay.
Means like n greater than equals to greater than not equals to, that is 10n. Means whatever the samples we have taken, that is multiply of that. If this is proportion, we have taken something like that, you have taken sample 10 and your total n is 1000. Okay, in that case, we can approximate by a hypergeometric distribution to the binomial distribution. Okay, but answer will be the same.
Thank you, sir. Thanks.
Anybody else?
No, we can proceed, sir.
Okay, this is the same graph we have shown here. We have just explained advantage, limitation of sampling inspection plan. We have already taken this. Now, particularly, we have focused on the single and double sampling plan in this particular lecture. So, This is the basic procedure that we have to follow here. What is that? In the if you will talk about the sampling inspection plan for a single sampling plan, you have taken you have some load, capital N is there. You have taken some sample, okay, of size small n, suppose, and in this sample you have find some defective items. Okay, that you can say define that is D. Okay, number of defective item that will be one or two, something like that in the particular sample. And customers already define those are required some particular product. They already define that particular C we have fixed there. Like three products we have defective. If this is there, we will not reject. We will not accept. Means if D is less than C, the process will go on. Means it will be accepted. If D is greater than equals to C, we have to reject the load. Okay, whatever the reason whatever the things beyond that, means we have to go for the rectify sampling plan. That is the other thing. But we have to focus on these. D is the number of defective from the sample that you have obtained or from the process, and C is the number of defective that is defined by the customers. Similar process we have to focus on here, like this is the example we have again taken from the Montgomery. Like if we have total n, okay, and we have some we have taken first sample D1, oh sorry N1, and in that sample we have some D1 if defectives that we have defined. And C1, if we have to take the decision based on the C1 criteria, so it will be it should define the condition. It should be follows: accepted the load if this is less than equals to, otherwise reject the load. If this is either not less than this, other not greater than this. So we have just we have to focus on the middle part. Means we have to go for second sample. We have to select the second random samples, and that will be, we can say, N2 that we have defined, and the second defective D2 defective will be there in the second sample. When D1 plus D2 defective from the first and second sample are less from the, let's say this was the 3 and C2 is something higher value of that. By combining these two samples, if it is less than this quantity, you can say that your product will be acceptable. Otherwise, you have to reject it. This is the main procedure for the single or double sampling plan. If you have to talk about the beyond that, like multiple or triple sampling plan, three samples you have to take there, or multiple samples are there. The same conditions you have to elaborate. Okay. And for the sequential sampling plan, the basic idea I'm just giving to you, we have to just focus as we can say in sequential sampling plan, we have to focus the product, means that will be acceptable at what level, means how much samples we have to take to get the dish. That is sequence, means up to that level you have to take the samples. Till then you will get the some particular quality of the product or some particular acceptable number of C. Okay, that is the sequential sampling plan somewhere. Now I think I have taken much time. Let's go for the R programming. If anyone has no queries. Any queries up to here?
We can proceed, sir.
Just give me 2 minutes, Dr. Sukal.
Sir, okay, it's fine, sir.
So shall we start, Dr. Sigil?
Yes, sir, we can start.
Is the font size is okay?
If you will increase a bit, sir, that will be much better. Yeah,
Fine.
yeah, that is fine, sir.
So as I told you all that I have just taken all the examples from the either from the open source or some books, that is Montgomery. Okay, so don't be worry about that the data from where you will get that. I will just explain to you. So there are some packages if you want to install like QCC package, quality control package is there. For the some part if you want to find the control chart limits or you want to draw the control charts or some other functions you want to do, these packages will directly give you the values. I will explain both the things like by using the manual method and by using the packages. Okay. So don't worry about that. Let me start from here. I have already installed it, so I will not install here. So first library QCC we have used to get the access from the QCC package. This is not of any use. Yes, first example, Montgomery book from page 232. We have taken here. Basically, it will tells us we have to define the mean chart and range or standard deviation bar chart by using the first data. Okay, and we have defined this data by using two different ways. Like first, we have taken the data by using the matrix form. Okay, let's say start here. Let me run this program. So as you will see here, there are 120 samples are there. Okay, by using different some sample subgroups and different sizes. Okay, number of column is 5. We have defined here means there are 5 sample sizes in these different groups. By using the command the length, then we have to calculate the means of these means from different rows we have to find, as these are the samples, so we have to it means standards are not given, we have to directly calculate from the sample. So this is the mean command, mean we have to calculate it from each row and then we have to find the range to get the range chart. Then we have to find the double mean. We have just written the values here. X double bar means combined mean of the these means we have calculated, and X bar means the range mean, means whatever the range we have calculated, then we have find the mean of that. Okay, if you want to see, just run these commands separately. So this is the 1.50 and mean for the R chart is 0.32. Now we have to define whatever the constant we have to use here, that is A2, D3 and D4. Okay, already mentioned in the book by specific sample size or specific sample group, taking them. Then we have to using these commands by using USL, we have to run here the chart LSL and these limits we have run here, control limits for our charts. Okay, if you will see here, I have just taken the mean plus A2 R bar for this one because we have just taken the standard values. There is no need to define the 3 sigma is there. Okay, standard values we have taken, so all the constant values are inside it, inside that. Now we have to plot that control chart by manual method. Basically, this is the command we have defined here. Plot, what you have to plot for the mean chart means we have to plot Type B, describe here the method you are describing these sample subgroup means. Okay, by which method you are defining, you have to type here like LB or whatever there is there. You can search question mark in the console window and you can get all the types of there. Y limit means from where to where you have to mention the limit on the y-axis and x-axis. X labels means you have to define something on x-axis and y-axis. Main command is used to describe something about the chart. So which kind of chart you have used there. Color for the color command and pitch for the size of the points. Okay. Ab line we have used to define the horizontal line on these X bar chart basically. You will see here the ab line H equals to X mean chart for color is green. So this is the center line. H is USL for the USL value means where you have to define this H value. Means where you have to mention these upper and lower limit, you have to define this. H is horizontal and you have to point that at whatever the USL we have calculated. That is USL X bar and USL LSL for X bar. Okay. This is the basic for one single chart, and every command we have used in the same fashion, so there is no need to explain it again. The same thing we have done for the R chart here. I'm just running the command. So you will see R chart is there. Some one point is on the center line or on the upper line, but is somewhere it is, you can say, the in control. But whatever the errors are there, you have to be focused on them. Means pattern of the chart that can be confuse you. Either it is in control or either it is out of control. So that knowledge will also be there if you have to take some decision from the basis of chart. The same thing if you want to do the by using the QCC package. So just the define data here and which type of chart you want to draw. X bar, R chart, or just standard deviation chart. And the basic, just first we will run the mean chart. It is somewhere looks like some attractive graph here. You will see some more values or some more data we have defined in this case. Center value, standard deviation, LSL, USL, number beyond the limits means somewhere the limits are beyond the limit. So it has taken the 0 to them. Number of subgroups are 25. So it will, whatever the package you will use there, one package is also there. That is 6 Sigma. Okay. That is also give you the some attractive graphs. Okay, either you can use the graph, but before using the graph means packages, you should know about the basics behind the means whatever the process to draw the graphs means to draw the control chart. You have to find the mean, you have to find the standard deviation, if samples are there, if subgroups are there. Okay, either this is something like that. R is just a calculator, whatever you will code, it will give to you. But behind process, you should know. If you know the process, either you will use packages, it will be fine. So this is for the R chart. Now the same data we have used, we have shown the same data, same example by using the data frame command, where by data frame, different kind of vectors or variables you can define in there. I just given the data here. Okay, 25 subgroups by different columns. Okay, by using different data, actually, if you have to add some more values, like you are not satisfied this is the correct value or not, or if you will get some data like some points are out of control, you have to remove them. You want to add some data, so you can use some other data as well in this graph. That is data 2 we have defined here beyond the point 26 to 45. So now the total subgroups will be 45 in this case. Okay, that is merge command we will use here to merge the board data. Means R bind means you have to bind the rows. Now if you will see the data here, it will be 45 subgroups are there. Again, the same method you will apply here. The merge dot means whatever the for this data you want to find the mean. So for the values where to where you want to define means you have to take the values from second to 6. First is the serial number you can define here 45. So it is of no use. 1, 2, 3, 4, 5, 6. Okay. Later, the first column, it will be 2 and 6 we have defined. So merge data cell, we have defined range and mean of the merge data. These are the mean and range. And then you have to find the combined mean and combined range. So you can use overall mean here, mean command. Then you can find the basically direct mean plus minus 3 sigma limits we have used here for the mean chart. Okay, you want to see that is USL and LSL for this case. For the range chart as well. Now, if you want to see both the graphs on the one sheet, then you can use the command parameter mf row, that row and column means two graph in one column. So just run this command, then plot the data. Okay, this is the one chart for the simple mean chart, you can say. When you will draw the second chart, it will be here. Okay, so both the graphs you can define here. You can, if you are, you can say that, we can say that if you want to define something like LSL, USL, or CL, some specific values at particular point, so you can use the text command there. Some in the next examples, I have used that, so I will show you. Second examples, we have shown for the standard deviations. So the same sample mean and standard deviation chart, we have to explain it again here. The data has been changed now. For the second example, the mean chart will be the same. Okay, one thing, the different command we have used here, let me explain. For the row means we have defined for this particular data, we have to find the row means of particular data using 2 to 6. Okay, when you have to find the range and standard deviation, like in here as well, we have used apply command is there, we have used. This is basically to get the range and standard deviation. We can specifically use the apply command. Okay, so these mean and standard deviation will be calculated here, and overall mean and range as well. You will see the values. Then you will draw the chart. USL and LSL for mean chart, USL or UCL or LCL for the range chart. Then again PMF row, mean chart you can define by using the commands, same command we are using again and again. Okay, so this is the mean chart for the particular data that we have used, and the for standard deviation chart. Legend basically there was some error in these command here, so that's why we so that I just hide here, but in the next example they are working. So in that, by using the text command, you will see here some particular value you can define inside the chart. Legend is used to define what are the colors or symbols you have used there. So description about something, you can be using the command legend can show in the chart. Then we have to draw the control chart for variables that is given on page 293 on Montgomery book. Sample numbers for 1 to 3, non-conforming the cans data we have. Then we have to find the sample fractions, means non-conforming means defective item D we have taken there in the sample size. So it will be sample size, sample fractions P we have calculated. Then you can find the P bar, and that is nothing but the 0.231. Next, we have find the USL and LSL for this case. If there are negative values, you can take the lower limit as a 0 and load the data. This is the graph for control chart for attributes, or P chart for non-conforming cans data. Now, if you want to add the lines, again you will use add line function. For the lower limit on the red and upper limit also red, and blue is the central line. Then if you will use the text command on this sample numbers, sample fractions labels, you will see here. Let me run this command. Let's see. Means by using the text, whatever the samples values are there, it will be shown at their points. Okay. Then legend, if you want to define LCL, UCL in the graph, so which colors you have used there, it will be shown on the right side, on the upper right side, you can see. The same data we have defined by using some other different commands here. Let me run it again. Okay, this is some commands are different. The data are same. Abline, we have defined the abline like the page paper, lines paper we have seen there. Or if you will use the grid command grid in the brackets, so some graph paper will be shown on the website. Again, these abline text functions, positions, ablines are same. For the LSL and USL, you can define here. CL, if you want to define, you can use that also. Text command we have used here. Let's see what happens. Trial UCL and CLCL means whatever the position you will define here, POS by using the POS command, the position will be decided by POS command. CX means whatever the size you want to take of this written text, it can be handled by this. Labels will be the same as we have discussed earlier. These were the two new commands that I just explained to you. Then for the NP chart, we have used the same data or different data, I think page number 300. So just let me run this command here. P bar means non-conforming cans, N bars or NP you can say. Okay, and we have defined separately. If you will see, N bar is 11.56 and we have defined separately. Then we have to find the P bar. Okay, 0.23, and here we have to use N bar. That is USL and LSL. We will get here. LCL will be 0 if it is negative. Again, plot the graph. Okay, so this will be the NP chart for non-conforming can. Same data we have used here. Okay, both will be follow the binomial distribution. And some other commands if you want to use here, or if you want to make this attractive, you can do something else with the data. Okay, it's using some different commands. Text, if you want to write something like the data points we have explained here. Legend, to write something on the right corner of upper side, UCL, LCL, we have defined. Text, like we have defined the N bar, but it is not N bar, basically it is the CL value. So we can change it as well. N bar, you can define as directly CL will be represented there. Okay, text, UCL, LCL. Just give me a second. N bar, you have to change here. Let me run it again. Okay. So by using different commands are there, you can use them to make your graph attractive. Then we have so the C chart, number of defects. Okay. Non-conformities we have shown here. C bar mean will be calculated. Sigma means it is using the basically Poisson distribution. So mean and variance will be same. It is we have defined separately. Then we have to define the sample number length 1 to n. Load the data by using abline. Legend should be there. Okay, like that. Here you will see, if you will not draw the legend, beyond that, if you will draw the data, one is outside the upper control limit. So you can say that this is the out of control limit. Okay, so this is basically the sample number at the 20, I think so. So you have to focus only this, why this is out of control, and whatever the assignable causes are there, you can remove them by identifying them. Again, you can draw the airline designs. Okay, print calculated values. If you want to print something there, just hold a second. So these commands use to calculate whatever the non-conforming values, upper control limit and lower control limit there. You can represent as well. Then U chart I have just missed. Just you have to do C bar by N, so you will get the U chart. But for that, I just explain you the condition. The sample size should be variable. Okay. In that case, you can do the U chart. Then we have cumulative sum chart. I just not discussed in the PPT, but let me explain it here. What is the cumulative sum chart? Basically, sometime it happens you have drawn like you have drawn the mean chart. Okay, and you have drawn the 3 sigma limits are there. So what happens sometimes it will look like that the data is in control, but actually no. We have discussed already this, but how to identify? Actually, what happens, whatever the small deviations are there, means less than 1 sigma, means 1 sigma or less than 1 sigma. If you want to find the deviation from the 1 sigma or less than that, you have to use the some other tools or technique like Q-sum chart. It will not be detected by the mean chart or range chart or the standard deviation chart, because they are not get the data, they are not get the variation, that slight variation. Okay, somewhere this is the same example we have. You can see on the page number 403 on Montgomery move SQC, Introduction to Statistical Quality Control. You will see there some one graph is also there that explain you the some data is in control, but actually it is not. Why the reason? Reason behind is that the deviation from the 1 sigma or less will not be detected by the mean chart. So for that we have to find the cumulative sum chart, and for that this we have some other technique as well, like cumulative sum method or VMask. Okay, I will not go for that, but I will just explain, just tell to you what is the Q sum chart. Leave it if you're not working. I have just used different method to draw the cumulative sum chart as well here. This is the data actually. Okay, 1 to 30. Whatever the difference CIs, we cumulative differences we have taken here for the cumulative data. Plot the cumulative values with some specific values. So before the values, whatever the differences are there, this cumulative up to here. Let me explain to you. Up to here you will see, if you will draw this data in the X bar chart, this will look like under 3 sigma limit. Here it will be UCL, and somewhere in the below side it will be LCL, somewhere it will be CL, like that. It will be CL like this. So it will not provide you the deviation, those are slight variations. Okay, when you will draw the cumulative sum chart, cumulative sum means it will take the cumulative values and it will draw that. Then it will show you the deviation about the sample groups or sample values of the rational subgroups. So this is the basic of behind this Q-sum chart. This is the another method by using the package, I think so, to draw the cumulative sum chart. Let's see it is working or not. Some error is there. Let me see again. Also taken. Yes, it has to be. Here, this is the deviation from the values h specifically we defined there. This is the h value basically. So this is the cumulative sum chart. Now, this is the chart. Basically, now we have to discuss the acceptance sampling plan. What are these? AQL, LQL, alpha, beta, we have already discussed. OC curve, basically, main part of this control sampling plan is the OC curve. So how to draw the OC curve? I'll just explain this random data we have taken here. And let's say we have generated data from binomial means probability of acceptance we have taken from the binomial distribution by using the sample size and particular proportion of the defective for the samples or the samples, and C is the acceptance number that is defined by the customers. So let's say probability of acceptance we have calculated. Now we have to plot P. What is the P? Basically, proportion of non-conforming items or defective items, you can say, with probability of acceptance. Type line chart, it will be shown to you. Let's this one. Okay, if you want to define some text here, like alpha 1 minus alpha by using the command, the text you can define here. Here it will be, you can say the producer risk on the upper side, and in the lower side it is the beta risk that is defined by the RQ. Okay, and AQL will be near to zero always, as acceptance or proportion of defective item will be less, the probability will be high. This is the explanation actually. When probability is too much perfect and that is rejected, that is the producer risk. If product is quality is too low and that is accepted, that is the consumer risk. Okay, so the lower side defines by beta and upper side defined by the alpha. Next in the topic we have process capability. If you want to find the process capabilities, we have taken some graph also here. What is the process capabilities there, how to use them. We have shown them by using the graph, using the ggplot as well. This is the process capability. This is the LSL, USL for the process capability CP by using some data that we have run here. Mean is 50, standard deviation is 2, upper specification limit 62, lower specification limit is 38, that is already defined. And we have calculated, already calculated actually, CP is 2 and CPK is also 2. So by using this command, you can draw this data by, as well here. The next graph is also showing the same data by using deviation in the mean, you can say, or shifted mean. This is up to here. Okay, so this is the graph we have taken where some specification limits are there and tolerance limit are there. Sigma is 2 for the standard for all the values. If you will see these graph individually, it will be shown clearly. Let me like this. So CP is 2 for the values. Deviation is changed. Deviation is same, but standard deviation also the mean is changed. Okay, whatever the mean we have defined there and whatever the process is there, the process has been shifted from the mean. Okay, that's why the target value is properly we have to show, we should define so we can get the idea it is in control or out of control. The same, I think the same graph we have shown, individual graph we have shown by using this command. Is create the plot lines. This one. Okay, two different deviation, two different process capability data we have shown here. USL, LSL also there. And some text we have defined, whatever the values are there, we have defined here. LSL, USL, process mean for the second one, process mean for the second one, 50 and 57.5. What you will take the decision about this? This is the graph A and graph B. Means you can say that somewhere graph A inside the limits, okay, but the your second graph, that is B graph, it is mean has been shifted from the center value, okay, or it is out of control from the upper side, from the, you can say, the upper control limit, okay. So if you want to control this, you can say, you can either you can increase the limit, 3 sigma limit. In case of 3 sigma limits, you can take the 4 sigma limit or 5 sigma limit, but by using that you can reduce the type first error, but type second error will be increased. Either you will go far from the center value, that reduce the type first error but increase the type second error. If you will come to the center value, means to the center line, that will increase the type first error but it will reduce the type second error. But somewhere you have to minimize this by using the some particular value of the deviation, 3 sigma limit, 2 sigma limit. That is basically a requirement of the process, or the manufacturer, or requirement of the customers, that depends on that. OC curve we have defined here by using the AOQL, average outgoing quality, rejecting load quality, alpha and beta, means alpha and producer risk. Let me define this using the ggplot. Okay, graph is not exactly equal. That should be somewhere commands error should be there. So, but it will be easily understandable. You can see that this will be rejectable quality load, that is beta risk. Acceptable quality load of this will be in this intersection point here, and this will be actually 1 minus alpha, probability of acceptance. And here this lower intersection point will be, you can say, the AQ, means when the proportion of defective is less, the probability will be high of the acceptance of this particular load. Now see the single sampling plan. Load size 2200, sample size we have taken this, and C is already defined. Number of non-conforming item, you can say. Proportion of defectives we have defined here, in different proportion of defective we have taken. NP we have defined. This is the one method. Either you can calculate the probability by using, we have used here the Poisson distribution, okay. So we have separately calculated it. Either you can use some direct command, or either use some loop function like for loop. You can define it here. Basically, that depends on the individual's programming. Is not the same method. This is mind mapping of individuals. I'm writing this one. You can use some other method, but the values you will get, that will be the same. So whole command I'm running here. Besides, when you will calculate the probability of acceptance up to here, total probability of acceptance we have shown, this will be like here, okay. Then probability of acceptance, we have to calculate the sum, final probability of acceptance to calculate the OC curve, average outgoing quality, alpha, average total inspection, how many total inspection you need there, ATI. Yes. For this individual particular data, we have seen this will be the OC curve, where you have some alpha, beta, 1 minus alpha, RQL. If you want to define them, you can use, we have used several command upper there. So you can use them individually. If you will feel that this limit is not actual, so you can change the limit of the plot, like let's see where up to where it goes. Yes, it goes beyond that. So let's say exactly one we are taking. 0.2. Okay, 0.15. You can rectify as well. Okay, so by using different modification, you can make your graph attractive. Other the things are same. This is the same graph or data we have used in some other methods, means to make this attractive. As well as with the OC curve, we have defined the average outgoing quality curve and average total inspection curve. Okay, means to get the particular number, if you have some number of defectives, particular number of defective, some how many inspections would be there, average outgoing quality what will be if you have some particular defective numbers, and OC curve we have already explained. Second data for the double sampling plan, we have already defined here N1, N2, probability of acceptance are there. We have calculated probability of acceptance for the directly, already we have calculated this here. And ASN for this case, AQL, AQL not calculated, some error will be there. So for the double sampling plan, you will see the OC curve and ASN number. Okay, ASN curve. Okay, for a particular proportion of defective, number of inspections, average sample number, what is how many sample number are required. OC curve simply. Third, this is the multiple or triple. If you have triple samples, you have to take the, if you have to use the triple sampling plan, for that also I have used some data to draw the graph here. That is, the graph will be somehow will be, you will get some better. The same thing we have done by using the acceptance sampling plan package. That is not that much crucial. Double or multiple, yes. If you want to compare, if you want to compare the double and multiple, single or double sampling plan, we have I have just taken one example here, who's showing by their numbers. It is not same. Like for the single sampling plan, you need 134 sample numbers, but in the double sampling plan, you need 88 individual. So the same double sampling plan is will be the good choice for the same data if you are finding the OC curve or ASN, something like that. This is the same. Now let me take to the another one where we can find directly by the commands packages, QC package. This is Six Sigma package. Yes. So there is besides the QCC package, there is a Six Sigma package as well. By using this, you can get the different control chart in attractive way. You can get the process stability indices. We have defined here graphs. You can take graph for the graphs. You have take the library graphics. You can see one graph. Okay, this process is going on. That's why it's not good. Let me end this process. So where it is. Is my PPT is visible to you?
Not yet, sir. Just click on your PPT, sir.
Is it visible now?
No, sir. It is our window is
Yes, sir. Yeah,
visible.
yeah. I'm showing. Sorry. Some process was going on. I have just ended that process. I just want to show you some functions there by using the QCC package. Let me find that. charts, yes. This is the QCC package. Require analyst to print, load, X bar chart. This is the different example we have taken here. Already explained in the okay. The same thing we are doing again and again. This is the graph of U chart. Finding that is not here. Okay, leave it there. I'm not finding that one. I just want to show something different to the audience. It is no, it is not there. Okay, so by using this, I will end my presentation. If you have any query, you can ask the question.
If you have any question, you can ask right now.
Sorry for the camera. Camera is not working actually. Some
It's okay.
technical.
Varun sir is there. I think Varun sir will have some query. And Harsh already there.
Dr. Shikhar and Dr. Sumit. Audible?
Yes, yes, you are audible.
Sir, very interesting session and very much learning from this session for all of us, and especially for me. Thank you for this session, sir. And thank you, Shikhar,
Thank you
Dr. Shikhar, for
thank you for being patient to stay here 2 hours long. And thank you for the Christ University and the team of and Sikhar Tyagi, Dr. Sikhar Tyagi for this interaction.
Sir, why you are here?
Thank you.
Okay, sir.
Thank you, Dr. Shikhar, for this kind of session. Thank you.
Thank you, bhai. I think we can wind up if no one has any question. So, Rita, we can wind up.
Yeah, okay. Thank you, Dr. Sumit, for such an insightful and engaging session on statistical quality control. Your deep expertise and clear explanations have provided us with valuable knowledge and practical skills that will greatly benefit our academic and research work. We truly appreciate the time and effort you have dedicated to this session, and we look forward to applying what you have learned today. Thank you once again for being with us and sharing your expertise. A gentle reminder, tomorrow at the same time, we'll have a session on machine learning with Dr. Kiran Kumar Pedipati. The link will be sent in advance. Thank you. Thank you, everyone.
Thank you very much. Thank you very much, Steve.